So last time we were looking at section 3.1 and we had taken a look at several different numeration systems. And I believe we were in the middle of a problem about the Mayans. Does that sound right? Well, in the middle of discussing the Mayans.
Example 6.
All right. So the Mayan example that we had gotten to is where we're going to take our numeral and we're going to turn it into one of their numerals with dots and lines and shells potentially. That's what we're looking to do. So when we did this over on the Babylonians, let me remind you what we did. This far right-hand side, this division scaffolding process, where we used the powers of their place system, right, their place value system, and we did some division. You can use your calculator as you do that. And then you end up finding the actual numerical values that we then need to represent in their symbols. That's the way it worked. And we're going to do that same process now with the Mayans. And we had done, where was it? It was right here. This right here to remind ourselves what our place values are in their system. So let me just copy this over here, except for the 0 at the top. And we're going to need these particular values. So we have the 144, 72,000, 360, 20, and 1. So whichever the largest one is that actually goes into our number, the 58,000 number is the one we're going to start with. So what's the first thing we're going to divide the 58,532 by? 7,200, right? So 144,000 is too big, but 7,200 is not. So we're going to try and divide it by 7,200. So what is that divided by 7,200? How many times is it going evenly? It goes in 8 times. And then we say, well, what is 8 times 7,200?
57,600.
Okay, so 57,600, and we subtract. So what do you get when you subtract that? 932. Okay, now one of the things to remember as we're working within our divisions on the left-hand side is that we have to represent every place value. So even if we come across a number that doesn't go in, we still use it. We haven't done that yet at this point, but 360 will be our next one, right? So we went from 7,200 now to 360. So how many times will 360 go into 932? Twice. Sorry, the 8 was supposed to go over here. I'm moving around my screen a little bit too much. All right, so what is 2 times 360? Yep, Emily?
Oh, I was just going to say, so instead of putting the 8 and the 2 on top where you usually put the number for division, you put it on the side?
Yes,
Okay.
because there's space, that's all.
Okay.
Because we're stacking things on top of each other, there's just no space on the top to do it.
Got it.
What I actually used to do when I taught this is I would actually just teach that we just did different division steps, but then it looks all disconnected in a disarray. The nice thing about having here is that they're all in order.
Okay.
So,
720.
720, yes it is. All right, and 932 minus 720 is 212.
Maybe not.
No, I have 212 written down.
Okay.
So yeah, you're good.
I did my head really quick.
Yeah, you're good. And then we divide by 20 because it's the next place value, right? So how many times will 220 go into 212? 10 times, and 10 times 20 is 200. Subtract and get 12. And our last place value is the ones place. How many times will 1 go into 12? 12. Okay, so the answers that we're looking for are on the right-hand side. We haven't actually finished the problem, but we have found the values that we want to represent. But now we need to represent them using dots and bars. I don't have any shells because I don't have any zeros over there on the right-hand side. So the first one up there, it was an 8. So I represent the number 8 by using a bar, which is worth 5, and 3 dots. And the dots always go on top of the bars. So I have 3 dots and a bar. That's 8. And then I need to represent the number 2. So how do I represent the number 2? 2 dots. The next one is a 10. How do I represent the 10? 2 bars. And the last one, how do I represent a 12? 2 dots and 2 bars. Now, this is correct. There's nothing wrong about what we did. But there is something weird about something that happened in what we did. Does anybody see the weird thing that happened? Emily?
It looks like it's 8 and then 12
Yeah, it does. Because that 2 and followed by the 10 didn't have any dots between them. Right? If it had said 2 and then 11, we wouldn't have this problem. We'd actually have an extra sort of dot in between the 2 dots and the 2 bars. But we don't. So we didn't do anything wrong. Everything we did is correct, but that doesn't mean that it's, sort of inherently appealing. Like it didn't work really well. Right? But that's not our fault. It's the fault of the system. So this is our correct answer for our Mayan representation. Dots and bars. Okay. The last numeration system that we're going to talk about, you are at least somewhat familiar with. It's Roman numerals. So you're most likely familiar with the I, V, and the X. So let's start there. How much is an I worth? 1. A V? 5. And an X? 10. So the letters that all come afterwards, again, you don't have to memorize these. I'm going to give you a card that'll show this piece when you get to the test. The letters that come afterwards all center around that same sort of patterning where we've got 5s and 10s showing up. So the L is actually 50. The C is 100. The D, 500. And then the M, 1,000. 1s and 5s everywhere. Now, what you may not know, because the way we use Roman numerals doesn't really necessitate it for the most part, is that we can do numbers bigger than 1,000, and they do have a way to handle that. These are the properties of Roman numerals. The first one you probably know, and then the second one might be new. The first one's a subtraction property. So in Roman numerals, they never write a digit 4 times. So anytime there's a need to write a digit 4 times, like the number 4, what they do instead is they write a smaller value, like a 5, and they write it in front, or they write the digit of 1 in front of the bigger value of 5. So if they wanted the number 4, they would write an I and then a V. And if the smaller number comes before the larger one, namely this is the 1 coming before a 5, this is understood to be subtraction. So you're getting the number 4. And it works, but it only works with the values that are close together on the table. For example, I don't get to do 99 by taking 1 in front of a 100. That's not allowed. Okay? 1 and 100, if you take a look, are nowhere near one another on this table, right? They're not juxtaposed. I can't do that. That's not an allowable operation. So what you see here is that the property directly affects only 4s and 9s, right? Because those are the ones where you would have things happening multiple times, too many times. So if we wanted to write 90, 90 has a 9 in it. So it's going to apply to where the 9 is. And we're going to find the value that's bigger than 90, namely 100, right? So the value for 100 is a C. And in front of it, we write the value that would occur that's 1 less. And I don't mean the number 1 less, but 1 less in the 90s in the tens place. Right? I need 10 less than 100, right? That's what 90 is. So the value 10 is an X. So 10 less than 100 would give me XC, and that would be 90. Because otherwise, we'd have to write a 50 and 4 tens. We don't write 4 digits that are the same. But 99, like I mentioned before, unfortunately is not going to be IC. That'd be great. And it isn't because I won't allow it. It's because they didn't do it that way. So we're doing it the way that they did it. So what they would have done is that they would have dealt with these 2 9s separately. So the first 9, representing 90, is represented as XC. That's 90. And the second digit, 9, you probably know, is IX. It's a 1 that comes before a 10. So in terms of this table over here, what you see happening is you see that you can get the 1 associated with the 5 or the 10. You can get a 10 associated with, let me change colors, a 50 or a 100. and you can have the 100, doing the subtraction process, associated with a 500 or 1,000. But that's it. You can't sort of jump to the further along in the table. Emily?
So could we also do 50 with 100 and 500?
It's always subtracting 1.
Okay.
You're never subtracting anything except a 1. So the only times you use the subtraction property is to subtract a 1 or a 10 or a 100.
Okay.
Those are the only numbers that come before a bigger digit to do subtraction with.
Okay.
Now, I mentioned this one that you probably aren't aware of it, but there is a property that's a multiplication property. So for larger numbers that you can't deal with what you've got before, for example, if you had the number 4,000, well, if all you have are these values, 4,000 would be 4 m's. But we just said that they don't use 4 m's, right? We got to do something different. So 4,000 is sort of the location where it's too big to deal with the way this is set up. So what we do instead is that we would write the number 4, and then we would write a bar on top of it. So if you have a single bar placed above any of the Roman numerals, it means it's times 1,000. And if you have a double bar placed above, it means it's times 1,000,000. So it isn't exactly like what we do with commas, but it kind of has the same feel, right? When we put that comma me in, we're doing it to make it easy to see that it's separated and it's in that different place value system. It's the same general premise. So if we had the number 9,000, that's bigger than 4,000. 4,000 was my cutoff, right? I have to deal with the number 9. And how do I write the number 9? IX. That's 9. And then the way I make it 9,000 is I simply put a bar on top. That's the number 9,000. Now, it's worth noting, because we're going to see some here in just a second, that it doesn't have to be just the whole number 9,000, like with zeros on the end. It could be 9,492. But only the 9,000 is the 1,000 part, so the bar goes over only the 9 part. And then the 492, or whatever I said, would come next, written just like we would otherwise. All right, so we're going to do the same process we were doing last time, where we take one of their digits and we find the number before, the number after, and then our corresponding number. So this is MCMX. The X at the end. Let me actually make one comment. We do need to pay attention to what's coming before and after things. Like, we need to know what the values are, even in order to do the number before and the number after. For example, this X at the end, if it's just X and it has something bigger before it, we're good to go. But if it had an X with the number 1 right before it, then it would be actually the number 9 at the end. So we have to be a little bit careful. The number X is actually 10. What's the number M? 1,000. So right now, I do have 10 as my last digit. So whatever I have, it ends in 10. And if I want the number that comes before it, it means that instead of the 10, I need to have a... What comes before 10? 9. I need a 9, right? What do I need to come before 10? I need a 9. So instead of that X at the end, all the stuff before is the same, MCM. But then in order to have a 10 become a 9, how will the 9 be written at the end? IX. So I just changed the 10 at the end to make it 9. Now, if I want the Roman numeral that comes after, the 10 at the end needs to become an 11. So what do I do to change the 10 into 11? We put the I after it. Yeah. So it looks kind of like we're doing the same thing, but the placement of it actually makes it quite different. Well, maybe not super different, but different, right? The I afterward means kind of like addition, and the I before actually means subtraction. All right, so we've already written out a few of these. I'm going to just write it down here again. MCMX. X we said is 10, and M we said is 1,000. What is the C? It's 100. So anytime you have a smaller number coming before a larger number, which we have that here, it's subtraction going on. So right there in the middle where I've circled the yellow part, I have 1,000 minus 100. So this part right here that's circled is actually equal to what? 900. So I have 1,000, and then I have 900, and then I have 10, which looks like that, 1,910. Okay, so now we're going to do a large number because I want you to see the bars and stuff play. So our number is 1,492,019. Now, you might say, first of all, hey, look, there's that million you were talking about. And it's true, there is a million in there. But again, unless it's bigger than 4 million, right, 4 million or bigger, I don't need the double bars because I can do it with a single bar. Just like if the number had been 3,000, I don't need any bars. I can do it with the 3 M's and take care of 3,000. Okay, are you all with me? Okay, so on this one, in a very real sense, we break things apart at those commas. I have 1,492 before the red line. And I can write 1,492 in their symbols, so that's what I do. How do I write the 1,000? M. How do I write 400? CD. Okay, so D's 500 with a C 100 before it. That makes it 400. 100 before 500. 90. Not 9, but 90. X, C. A 10 before a 100. And then 2. 2 I's. And because this 1,492 is actually in the thousands place, right? That's what I really have because I separated it with a red bar. This is all got a bar on top of it, but just this part. And then what comes next will not have a bar on top. It's just 19. So again, we do it place value at a time. How do I get the 1, the 10 that's here? X. And then how do I get the 9? IX.
What was your reasoning for the bar above? Because we're working with the 1,000.
Yeah, so basically what I created here was the number 1492. The bar above means it's times 1,000. So that puts it into the right place so that I've got 1,492,000 instead of 1,492.
So when we work with a number in the millions?
It will. If the number in the millions had been too big, like let me make one up just so you can see. Let's say the number had been 5,492,019. I don't want to change too much. I just wanted you to see just the part I need. So I would still have the break here. But I'd actually have a break here because the number 5, I don't have a way to write 5,000. So if I'd left it off, I can't do a 5,492. That's just not an option. I don't have a 5,000 symbol. So I have to break it again. The way I would get the 5 symbol is, of course, a V, but I'd put 2 bars on top. And then the 492 would be much like we did before, so CD, IX, II, and it would have 1 bar. And then I'd have my 19 at the end, XIX.
And then it would have 1 bar. 492 would have a bar.
It's in the thousands place. It's 492,000 where it's located, right? This is in the thousands spot.
Got it.
Yeah. So we're only using the bars when they're absolutely necessary, right? That's what we're doing, only using them when they're absolutely necessary. But when they do come into play is because they're going to have something bigger than a 4 in that thousands place or millions place. Well, 4 or bigger.
That's what I...
Yeah, you're looking for something 4 or bigger in the millions or the thousands place in order to use bars.
How come our V would have 2 bars instead of 1?
Because it has to be times a million, not times 1,000. If I only put 1 bar on top of it, it would be 5,000. Putting 2 bars makes it 5 million.
Okay.
Yep. Is that good? I know it's a little different. We don't use them very frequently, see them used very much, but that's them. All right, we're going to talk about a manipulative system that I know you've seen before, and I should have brought my blocks. I'll try and remember to bring them on Friday. So base 10 blocks are very helpful in helping kids understand the difference in size, and in particular, really about place value. So when I think about the number like over here where I had, say, 492, the 4, the 9, and the 2 are really not 4, 9, and 2. They're 490 and 2. So I can't somehow combine the individual numbers in any way because they're in different place values. And that's what base 10 blocks do, is they give us a visual for place values. So there are 4 of them that we're going to talk about. The first one's called a unit, and they look like little bitty squares. When I bring them, I'll show you. They're just little bitty squares. And then what happens is in a very like Lego-y sense way, if you were to attach 10 of the little bitty squares to each other end to end, you would create something called a long. So the long looks like the same thing, but just 10 long. Okay? So a unit is in fact the ones place, and it's worth 1. A long is worth 10. It's the tens place. If you stacked 10 longs together, not end to end, but sort of tall, right, the way that I've drawn them, you would end up creating a very large square like this. Okay, so if you can imagine there's 10 of these longs in here like this. Okay? They're filling it up. Mine don't look perfect, but you get the right idea, I hope. And this is called a flat, and it's worth 100. And the last one is a block, and a block is a three-dimensional shape. So again, what we would do is we would take these flats and then we'd stack them sort of deep, right back like into the screen. And we'd have something that would look something like this. The nice thing about this kind of a representation is that there's a very clear reason to think that if I had 492, I'd have 4 flats, 9 longs, and 1 unit. And there's no way that I can think that I would just say, hey, look, I've got this one, and I'm just going to put them together. So this is what happens sort of visually speaking for my 7-year-old right now. She struggles with the different bills, right? So she gets paid a little bit of money each week. We're working on that, learning how to save and give and spend money. And if I give her a 5 and I give her a 1 and she starts counting things, she counts them as 2 because there's 2 bills. There's no size differentiation for her to see that they're different. It's not like coins, right? They don't think about it quite the same way because they look the same size. I know they got different numbers on them, but that's not what we're talking about. It's the size thing. So this has this very nice visual, concrete, kinesthetic thing where you can touch and feel that the sizes are different. So what we're going to do in some of these is we're going to think about what happens if we take these base 10 blocks, but they don't have 10s. Okay, so again, our system is a base 10 system. The unit's worth 1, the long is worth 10, the flat is worth 100, and the block, I didn't write it. What do you think the block is worth? Yeah, it's worth 1,000. This is all because it's based on the number system having a base of 10, because we have 10 fingers, right? As we talked about last time. So what would we do if we actually had only 8? Well, instead of having powers of 10, we'd have powers of 8, right? So it says, in base 8, how much would a unit, long, flat, and block be worth? Well, the first one's always worth 1. Units are always worth 1. That never changes. But the long would be formed by putting 8 units together. So the long would be worth 8. And then if I stacked 8 longs together, what would I have? 64, right? Namely 8 squared. And then if I stacked 8 of the flats together, I'd have 64 times 8. What's that one? Gee. 512, yeah, that's what I have written down. It's 512. And that would be 8 cubed. It's a three-dimensional shape then. So our place value is built upon a base 8 if I'm working for 8. So thinking about it from that perspective, B wants to know if I had these manipulatives, really, like I really had a unit, I had, this longs that are worth 8, these flats that are worth 64, and blocks that are worth 512, what would 237's numerical value be? So kind of imagine that you have a bunch of Legos. This question is asking if you have the Legos where there's 2 flats, 3 longs, and 7 units, and you break them all apart into their individual little bitty Lego pieces. How many pieces do you have? Can you fathom that? So what happens is we have 2, 3, and 7. This is the 1's place, the 8's place, and the 8 squareds or 64's place. So my 2 flats, each of them worth 64, mean that I have 2 times 64 individual units within those flats. My 3 longs mean I have 3 that are each 8 long. And then I have the 7 units, so 7 times 1 are just 7 at the end. And if I were to break them all apart, that's the equivalent to what I've written down in a multiplication statement. So we're going to grab a calculator, do a little bit of multiplication and addition. And what would 237 be in base 8? One 24, 24, and 7. I'm sorry, 128, 24, and 7, I mean. What's the sum? 159. It's 159. So there's 159 individual units, or kind of like the smallest denominator Legos, if I've built it with Legos. Now this question that we just answered, we're going to see asked in a couple of different ways. One of them might be what I just asked. The other one might be like this, where it says, what is 237 base 8 in base 10? Okay, it means I'm breaking them down into their individual units and how many individual units do I have. So that's how we're going to think about that question. Now we are going to work in other bases. We just talked about base 8. So we're going to talk about a couple of other bases. So think about with me base 10. In base 10 we had 10 numerals. They started at 0 and they end at 9. So while there is a 10 in base 10, it's not an individual numeral, it's 2 digits, right? So what you need to remember is that there's no numeral 10 in base 10. There's no numeral 8 in base 8, there's no numeral 3 in base 3, there's no numeral 7 in base 7, there's no numeral 12 in base 12. So whatever base we're working in, it does not have its own namesake as a numeral. It stops one short. So if we were dealing with base 8 just a moment ago, we'd start with 0 and we would end with 7. So we're going to think about what happens in these bases and what happens after we hit, like the end of the numerals that I do have. So base 3 has 3 numerals, but it doesn't have a 3. What does it have? 0, 1, and 2. And once I hit 2, I've run out of 1-digit values in base 3. So now after I run out of 1 digits, I have to move to 2 digits. So what do? Well, it becomes 1, 0, and then 1, 1, and then 1, 2, and then 2, 0, 2, 1, and 2, 2. I just keep increasing until I run out each time, and I run out right before I get to 3. Now the problem here with the situation here with 2, 2 is that I've maxed out. That is the biggest 2-digit number in base 3. It's 2, 2. What would I have to do once I run out of 2-digit numbers? 3 digits. So I end up with 1, 0, 0. I'm going to do my best, and I ask that you try to do your best too. That number at the end is not 100, because it's not hundreds. It's 1, 0, 0. So we're going to identify it by the individual digits names instead of inferring our base place value system on it. Because if I say 100, it means that I'm in base 10, right? Hundreds, that word there. So that's not 100 at the end, it's 1, 0, 0. And we'd keep going through the same process and we'd continue on as we go. What about base 7? Oh, yes, Emily.
So I went ahead and did it all the way to 122.
Yep.
Then after 122, we would add another 1 to it, and it would be 1, 0, 0, 0.
Actually, after 122, you'd get to 2, 0, 0.
Okay.
122 would become 2, 0, 0. Now, once you got to 222 is what you were thinking of,
Yeah.
then you'd have 1 with 3 zeros after it. 1, 0, 0, 0.
Okay.
To give you a 4-digit number. Yep. Base 7. So it starts at 0, and it's going to continue to what? 6. What happens after 6? 1, 0. 1, 1, all the way to 1, 6. And I do 2, 0, 2, 1, all the way to 2, 6. And eventually I would get my biggest 2-digit number. What's my biggest 2-digit number? 6, 6, right? and then I'd have that 1, 0, 0 again. So there's some questions in your book where they say, write the first, I don't know what the number is, I'm going to make something up, write the first 9 digits in base 7 or something like that. You wouldn't put these dot, dot, dots, you just write the first 9 of them. I don't really care whether you start with 0 or 1. I kind of feel like you should start with 0. They kind of start at 1, so I don't care. Pick your favorite. It doesn't matter. 12. Now 12 is interesting. How is 12 different than considering 3s and 7s? Yeah, it's already a 2-digit number for us. What were you saying over here? Same thing? Okay, good. Yeah, so it's actually bigger than our place value system, right? So can you imagine you had 6 fingers on each hand? Okay, that's base 12. So in base 12, what do? Well, we actually need more digits than we have, right? We only have digits up to 9. And we need some kind of a digit for a 10 and some kind of a digit for an 11. Are you with me? So I'm going to tell you what this book does. It's not my favorite thing, and it's not the same thing that my contemporary math book does when we do this, unfortunately. So my contemporary math book goes to letters A, B, C. This book doesn't. So we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then it goes 1, T, T for 10, and E for 11. 1 T, 1 E. You might say, okay, well, what happens if I get to a 12? What if I actually needed that? Like I was looking at something bigger, and it uses a W, and it doesn't give you any examples in the book any bigger than that. So, I mean, I guess it sort of works, but I don't really feel like it's that great. Hallie? Oh, do you have not have a question? Okay.
Oh,
1 T, 1 E. And then I'd run, that's my biggest I didn't say that right. I wrote those wrong. I was already ready to go to the 10s. T and E. Please erase those. I totally messed that up. T for 10, E for 11. After that, I've run out of single digits, and then I go to my 2-digit number. I was already ready for 2 digits. And I do 1, 0, 1, 1, all the way up to 1, 9. There's my 1 T and my 1 E. Now, just because I've written them out, what would the biggest 2-digit number be in base 12? What's the biggest 1-digit, single digit? E. So what would be the biggest double digit?
1 E.
Nope. EE. It'd take you a while to get there, but it'd be EE, much like our 99, right? And then after that 2-digit number, we'd be forced to move into 3 digits, and we'd have 1, 0, 0. Okay, so you might be thinking, okay, why are we switching number systems? So there's a couple of reasons. We're going to do some examples with these, but there's a couple of reasons. Number one, there are other number systems you use. You just don't think about them cognizantly that way. One of them is your clock. We don't worry so much about the fact that we use 1 or 2 digits, but we work on a base 12 clock system. And we also work within our clock on a base 60 clock system. 60 minutes in an hour, 60 seconds in a minute. But then we've got the 12 hours before we repeat the hour count, right? So we're working in those. Base 2, do you guys know where base 2 is used? It's probably the most prevalent one. It's hidden. It's in every one of your pockets. Programming and electronics is all base 2. Well, maybe not all, but a lot of it's base 2. Zeros and ones, ons and offs, okay? Another thing your electronics are sometimes programmed in is called hexadecimal. That's base 16. So that's another one. So there are pieces of things that we do that have this sort of cyclic nature that are not based upon our base number 10s. That's good, but why are we doing it here? Well, part of what we're doing here is on purpose to make you a little bit uncomfortable. And here's why. It's really easy for me to ask you in base 10, what's the biggest 2-digit number? And you're going to tell me 99, and it's no big deal, right? What comes after 99? 100. What comes before 99? 98. Easy peasy, no problem. But when you've got kids in your classroom, the age of my little girl who's 7, that's not always the easy question. Because they don't actually understand our base system like you understand it, because you've been working with it for 20 years. Maybe not all 20 at this point, maybe 17. Probably since you were at least 3. You've known a little bit about this number system, right? And your knowledge has built upon it. Well, they haven't worked with it that long. And so part of this is to simply put you back in that position where you have to really think about what we're doing and why, so that you could think about the same sort of thing if your kids were asking you the similar type of questions. So when we see this number right here, 1, 4, and it says base 5. And the question asks us, like the ones in our other numeration systems did, what comes before and what comes after. That's harder to do because you're not very familiar with base 5, right? So have you ever heard a child go start counting and they get to like 19 and they go 18, 19, and they don't go to 20, they go to something where they, actually that's not a good example. Let me use 20s. So they get to 28, 29, and then they say 2010, 2011. Have you ever heard a child do that before? Because I have. Because all they're doing is they're trying to repeat that same verbiage, but it doesn't quite work like that. So that's kind of what's going on here. We're running out of digits. What do we do about it? So what comes before 1, 4 in base 5? It's 1, 3. That's the easy one. But 1, 5 does not come after 1, 4 because there are no 5s in base 5. So what comes after 1, 4? 2, 0. Now, when we're doing this, I'm just writing them in order, but when we're doing this, we need to write down the subscript next to it. And your book uses the convention where it actually writes it out as a small, like a subscript word. So that's what we're going to do. It's 1, 3 base 5 and 2, 0 base 5. So these are our two answers, the one that's before, the one that's after.
So whenever we have a base, we can never have that number. So
Correct.
If it's base 5, 5 does not exist.
Correct.
Okay.
Yes. B. Oh, Jordan, yes.
I don't know, I don't follow this at all, but why would you not go like 1, 6? Like, you not just. I don't-
So it's kind of like asking, well, why don't you do 110? Why do we say 11? Right? Why, when we get to the end of 9, we have to expand to 2 digits, correct?
Yeah.
And our 2 digits have to include only the numbers that are in our place value system, 0 through 9. The same thing's happening here. This place value system with base 5 only has digits from 0 to 4. So there are no other digits in this world. This is the world where you only got one hand.
Okay.
That's it. There are no other digits. There are no 6s.
Okay.
Part B, T00. So this is the number in the middle. It's actually the number after that's the easier one. What comes after T00? T01. That one's the easy one. They're always going to have one easy one and one that's like making you think. Okay? Comes before. Ooh. You got to come before something that's got a 0 on the end.
Is it 9? Yeah.
Okay, give me a thought. What do you think?
The last digit would be E.
The last digit would be E. You're right, Emily.
And then
But isn't 12 W though?
12 is W. No, 12 is W. T is 10. There's a 10 here. Teen. Good grief. 10. That's the number 10. And then these are the numbers 0. Right? Just 0. They're 0.
It would be TE?
I have another E. And there's a 9. Okay, so you're like, what is she doing? Okay, I want to do what happens in our number system when we have something and think about it. What do you do when you have the number, we'll just do 400. What do you do when you want the number before that? We've got to decrease the 0. But there's nothing to decrease it from. 0 is nothing, right? So you move to the far left and you regroup things and you say, okay, this 4 needs to go away. It needs to become a 3. That's what happened here. My 10 has to go away to 1 less, and 1 less than 10 is 9. Right? I don't mean equals. It gets marked out. Goes away, 1 decreases, and it goes to a 9. But when I borrow in this system, I have to borrow all of it, right? I want to write down the number in our system that we just borrowed. This is base 12. Okay, so imagine my picture that I had before with the base 12 blocks. You had a flat. You had 10 flats. Okay, so 10 of these big old giant squares. Okay, 10 big old giant squares. And you take one of those squares and you break it into the individual long pieces. It was a 12 by 12 square, right? Because I'm working in base 12. So when I broke it into the individual pieces, I now have 12 long pieces.
And E is
That's
11.
and E is 11. So this is the 12 long pieces that I would have when I broke it apart. So now I have 12 long pieces. But I need to borrow from that, right? So I don't really have 12 long pieces because only one of them needs to be changed in for some individual units. So now I have 11 long pieces. So one of those longs now gets broken apart into the individual Lego units that it had. And it had 12 before, right? There was 12 of them. This is the equivalent of what I have. They're just all broken apart now. Now I have 9 flats, I have 11 longs, and I have 12 units. That's what I had to go backwards one value. Now the 12 I have to subtract one from, like that's the whole point. This right here is actually equal to T00. And I'm taking them apart. So I take one away, and this will now have, because that's what I was looking for is the number before. If I take one away, this is an 11. So there's the 9 in front, and then there's the E's because they represent the number 11 for us. And you feel like this is very frustrating. So imagine what your kid feels like when you say, I've got 400, and I need to take the big old square, and I need to break it into the individual longs, right? How many longs do I have? Well, I have 10 longs. And then I need to take one of those longs away. So now I have 9 longs. And I need to break apart into individual little pieces, all those individual little units, right? And that will give me 10 of these. And then I need to take one of them away. And when I take one of them away, I now have 9 of them left. And I get the number 399. That's the number that's before. So this is a before and after kind of question. Now, if you remember in the numeration systems, the other thing that we did with before and after question, with the numeration systems after we did the before and the after, is we changed them into our numerals or from our numerals back into their numerals, right? So we turned something back into Roman numerals, or we took something that was Mayan and turned it into our number. So what we're going to do next is exactly that. We're just going to do one more set of these, and we'll stop with example 12. So 12 and 13 will be for next time. So what we're going to do on this set is we're going to take whatever their base is, base 5, base 12, base 6, base 2, whatever it is, and we're going to turn it into base 10. Okay, so really what we're doing here is that we're breaking things apart. We're taking longs and flats and blocks and we're breaking them down into the individual unit pieces. So what we do is we put the numerals into expanded form. We consider the base. Is it base 8? Well, then there's powers of 8. Is it base 5? Well, then there's powers of 5. And then we multiply out the expanded form. In essence, what we do is what we did right here. We put it in expanded form, base is 8, and then we multiply it out. So here's our first one. It is base 2. So what I would encourage you to do to start with is to make the 4 lines and put the digits that they give you in them. 1, 0, 0, 1. And underneath, put the place values. This is base 2. Now there's always a units place, so it always starts with 1 on the far right. And then we have the place value we're working with, so it's 2. And then it's powers of 2. 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, however far you need to go. 2 cubed is equal to 8, and 2 squared is equal to 4. And then you're going to multiply each value in the place system, right, the 1 on top, by its value that it holds. Right, so these are 1 times the 2 cubed, or 8. Actually, let me write 2 cubed for now, just to keep it clear. I have 0 times 2 squared. 0 times 2, and 1 times 1. So I'm multiplying each numeral from that I was given, the 1001, by the place value where it lies. Like I said, this is 1 times 8. Whoa, not 80, 8. These are zeros in the middle and a 1 on the end. So this is 8 plus 1. 1001 is 9 units. That kind of makes sense because these would be very tiny little flats and longs, right? Longs would only have 2 pieces stuck together. Flats would only have 4 pieces stuck together. Blocks would only have 8 pieces stuck together. So let's do one in base 12. That's that T00 we saw before. Now you're welcome to write the T in. You're also welcome to write that it's equal to 10 because our point is that we're going to be breaking things apart. It is in base 12, so I have the 1's place, 12's place, and 12 squared, or you could continue if you had to. 12 cubed, 12 to the 4th. What is 12 squared? It's 144. So I take each value, so t, which is 10, times 12 squared, and I'm going to write the zeros in just so that you can see it. 0 times 12 and 0 times 1. I know there's zeros, and if you don't write them, it's okay, but you would normally have other numbers there, or potentially. And then we would have 10 times 144, and these are both zeros. 10 times 144 would be 1,440. So if I had 10 flats, and each flat was 144, that's 10 times 144 units. That's what that is. So what we're going to do next time is we're going to take our number and we're going to piece them back together. So instead of breaking them apart like we did here, we're going to piece together things that are flats with another system and longs in another system and blocks in another system. And we will stop there.